with a standard state there. So if it's delta G of standard states, that's equal to minus NFE standard state. Plus RT ln of Q. And then let's just divide everything by minus NF so that we have measured, this is the measured potential. This is the standard potential minus RT divided by NF times ln of Q. That's called the Nernst equation. Nernst. Kind of fun to say, especially if you are. Nernst. So this is really nice because this number right here is relatively easy to measure. All you need is a voltmeter. So you can directly measure this number right here for a reaction. So that gives you a connection between something you can easily measure and the concentrations of reactants and products. So that can be really nice. Now what if the reaction is at, equilibrium? What changes here? Well, delta G, what do we know about delta G in equilibrium? 0. So what do you think is true about measured potential at equilibrium? It's also 0. So at equilibrium, 0, and this number doesn't change, that's a constant. And this RT over NF, that's really just a bunch of constants in the n value. But Q becomes K. And, yeah. So therefore, the standard potential, which is something you can calculate from tables, is equal to RT over NF times ln of Q. So there we have a connection between the standard potential that you can calculate from tables and the equilibrium constant. All right, so let's see what we can do with that. Let's do a problem. I can't put this up on the screen, so I'll just write it. You know, our campus has 2 power sources. We get electricity from the north and from the south. They both come in. There's a big switchgear thing back in the back of campus where all the power comes in. So we're supposed to have lots of redundancy. Power goes off to one area, you just switch over to the other area. It's surprising how often we lose power here, even though we have 2 separate sources of power. Okay, here is a reaction. Nickel fluoroxide reacts with 4 moles of hydrogen ion and 2 moles of solid silver to make nickel ions and 2 moles of water and 2 moles of silver ions. All right, so there's a reaction, and the standard potential they've already calculated for us to be positive 2.48 volts. And then the problem tells us that the pH right now is 2. And they tell us that the concentration of nickel ion and the concentration of silver ion are both the same, and it's 0.03 molar. The question is, what would we expect the measured potential of the reaction to be? Okay, so which equation over there are you going to use?
First one.
A Nernst equation. See what you can do with that. Nernst. Yeah, unless I tell you otherwise, assume 25 degrees. But remember, what kind of temperature units do you need to use here? Kelvins. Yeah, so that's a big part of this problem here is, how do we know how many moles of electrons are being transferred? Because we don't have the half reactions to look at. But we can pull those out, right? I mean, one of the half reactions involves nickel 4 oxide and hydrogen ions and nickel ions. But another one, there's silver and silver, right? So we can look at that half reaction on our table. So this half reaction is on the table, silver plus 1 electron goes to silver solid. So that's one of the reactions on the table that you can find. So this one is obviously being multiplied by 2, isn't it? So therefore, I know that 2 electrons are coming out of the silver when it gets oxidized to silver ions. So it's 2 moles of electrons. Yeah, so you can usually break
Paano
apart
makuha ng electrons?
the reactions, the half reactions, if you don't already know this.
Sa AG at sa...
And notice in the calculation I did for Q, I left out the solids, because they don't go in the equilibrium law, and I left out the water, so it's just the ions that go in. How did I know the hydrogen ion concentration was 0.01? Yeah, pH 2, that means hydrogen ion concentration is 10 to the minus 2. Any other questions there? What was what? Oh, 2.37 volts. Probably behind the body. 2.37 volts. Okay, have a good weekend, everyone. Thank you for coming on this spot.